So you can transfer energy by moving particles from place to place, like a baseball moving through space is particle transmission of energy, or you can transfer energy using waves. And the concept of a wave is that you have some thing oscillating, and I don't want to worry too much right now about electromagnetic waves, okay? I want us to just focus on mechanical waves. Electromagnetic waves are what we're going to be studying in detail next year in Physics 30. But mechanical waves, which is what we want to focus on here, have some physical medium, some physical substance that does some oscillating or vibrating or jiggling or whatever you want to call it, and as a result, the energy goes through it. So if you hang on to one end of a piece of rope and I stand 15 feet away from you because that's how long the rope is, I can transfer energy to you by just shaking the rope back and forth, and we'll get a wave moving through it. The wave doesn't have to be a perfectly synchronized wave. I could just kind of be randomly shaking the rope in all kinds of directions. And as a result of that, the energy will go through it. We did talk yesterday about the fact that there are longitudinal waves and transverse waves. And to begin, we're going to go right now into the atrium area so that I can demonstrate that to you. This slinky is suspended by a bunch of strings, but some of the strings have broke, so I've had to kind of coil some up. On this side, I have a little spring, a little kind of like an upside down pendulum made of metal. And if I pluck it, you can see that wave energy move left to right. And those are compressions that you're seeing. You can see that visually, right? If you could take a snapshot right now and you measured the distance between those compressions, you would be getting the wavelength. And you can actually determine the frequency by looking at the frequency of this oscillating arm. And if you took, leading up to yesterday's stuff, if you take the wavelength that you measure times the frequency that you measure, you will get the speed that the wave is moving at. So I've reviewed everything that we've covered now up to and including the universal wave equation, which is speed equals frequency times wavelength. And that leads us now to the problems. I got 5 nodes 1 year, but you have to be moving so fast to begin with. And we will learn a little bit about this today because some things have natural frequencies. You can't just take that spring that we had out there in the atrium and expect to get 3 nodes. You have to be twirling it with a certain frequency to make that happen. It's like musical instruments, the strings on musical instruments. They only vibrate at certain natural frequencies. And by the way, if you take a guitar string, and I know I'm getting a little off topic, but if you take a guitar string that's mounted here, I mean it's mounted and it goes over some frets, but there's a guitar string that's pulled straight, and I take that guitar string and I pluck it down this way and let it go, I create a standing wave with 2 nodes. All that happens is this guitar string vibrates back and forth between these 2 positions. If I take that guitar string and instead put my fingers in this position and this position, and I pull this down and this up and let it go, then I'm going to create a standing wave that has 3 nodes. Does anybody have any questions from yesterday's problem set? All right, we're going to move on. I'm going to give you today's lesson. I have a problem with my notebook software. It's not operating properly, so I'm going to just have to teach this using Microsoft Word, but that's okay. So I really like this unit, but it does kind of dance all over the place from thing to thing, and it's not, like I said the other day, it's not as linear as some of the other things that we study. There's a lot of overlap, in other words, between the things that we do. I'm going to start off here by talking about the speed of sound in air. It turns out that the speed of sound in air depends on the temperature of the air, and that probably shouldn't be a big surprise to you. Within a certain range of temperatures, this is the formula you can use to find the speed of sound in air. And the reason why this predicts that the speed of the sound increases as the temperature goes up is sound is a mechanical wave produced by collisions of air molecules that carry that information in a ripple, in a compression, just like this thing. Just like the different pieces of this spring collide with the next piece of the spring, a certain piece of air or slice of air collides with the next piece or slice of air. But at a higher temperature, the molecules are moving faster. So there's kind of more chaos happening, but the time between the collisions is going to be less, which means the overall speed of the sound is greater. At 0 degrees Celsius, the speed of sound is about 331 meters per second. Either on Monday or Tuesday, we will do an experiment together in the lab where we determine the speed of sound. And we're going to end up determining the speed of sound in this classroom. Right now, the temperature in this classroom is 20 degrees Celsius. So if you were to put 20 into this formula, it's not a complicated formula. And by the way, it's not on your formula sheet, but I would give it to you for exams. In this room, it's actually 20.4 degrees Celsius right now. Wow. According to the thermostat. I don't know how accurate that thing is. But if I add 0.6 times 20.4, the speed of sound in this room is about 343 meters per second. And if you think about the physics of trying to measure that, that's going to be a pretty difficult task. There is a way to determine the speed of sound. I don't want to go outside and do this, but there is a way to determine the speed of sound by measuring distance and time. And it would work well on a day that's fairly cold, even colder than today, because the colder the day, the slower the sound, according to this formula, and it's easier to measure the time. But what you have to do is stand maybe 100 meters away from a wall, big wall, shout, and you will hear an echo. I mean, you have to find a circumstance where you're going to hear an echo. And what you would do then is measure the distance from you to the wall and double it and divide by how long it takes between you speaking and hearing the echo. And that would give you the speed of the sound. You have to double that distance because the sound travels to the wall and back in order for you to hear the echo. That's what an echo is a sound wave bouncing off of the wall and coming back. It's like that wave that when we were in the atrium, when it hit Alex's hand, it reflected back. That's what's happening during an echo. So let's go through and let's do example 1. What is the speed of sound in air at 25 degrees Celsius? Well, as I said, my notebook software is not working, so I am just going to do this on my calculator. You will have to decide what it is you're going to write down. It would be 331 plus 0.6 times the 25 degrees Celsius. So about 346 meters per second, which is pretty quick. By the way, how many of you have heard that old tale that when you see lightning strike, if you count how long it is in seconds until you hear the thunder, you know how many miles away the lightning struck, something like that. It's totally wrong. It's totally wrong. There's a difference between when you see the lightning and when you hear the thunder, even though they happen at the same time, because the speed of light is so many times greater than the speed of sound. Turns out it's about 1,000, about 100,000 times greater, roughly. So when you see the lightning, the light's hitting your eyes pretty much instantaneously. It does take a little bit of time for the light to travel to your eyes, but you don't notice it. And that means that the time that you're measuring the delay of is actually the time it takes the sound to travel that distance. Okay? So for each second, let's say we're 25 degrees outside, for each second of delay, it's traveling 350 meters. In 3 seconds, it travels about a kilometer. About a kilometer. So when you count, you see the lightning and you count 1, 1,000, 2, and you hear a crack, it's only about 600 meters away. That's where the lightning struck, about 600 meters away, because sound is traveling only at about 300 roughly meters per second. Just so you know. How long does it take sound to travel 2 kilometers through air? Well, let's say the speed of the sound in the air is 335 meters per second, or that's given to you in the question, and it's 2,000 meters. You should know how to do this question. It's a Science 10 question, isn't it? Science 9 question. Speed equals distance over time. If we take that 2,000 meters and divide by 335, we get the time in seconds. It takes about 6 seconds. Which means, very roughly speaking, if you have to wait 6 seconds between seeing the lightning and hearing the thunder, that lightning struck approximately 2 kilometers away. It's not exact because it does take a little bit of time for the light to reach your eyes, but it's so small, it's pretty close. Any questions with 1 and 2? Number 3, a tuning fork has a frequency of 256 and it's sounded. What does that mean? It means I take a tuning fork, frequency of 256. This is probably 256, 320. $256. So I sound this tuning fork. Probably don't hear that very much. I find my knee works better. I've got a plastic knee. I'm just kidding. I don't have a plastic knee. And you know what? It does hurt a little bit. No, I don't have a plastic knee. It would be cool because then I could just do that, right? Smack. No, I have a real knee. I might need a plastic knee one of these days because of this. But no, it just, if you practice that one. Okay. So that's what it sounds like. What is the distance between successive compressions of the sound wave in air produced by this tuning fork at a temperature of 25 degrees Celsius? I'm not sure why there's a bracket there. So in order for you to answer this question, and if you're watching on video, I apologize, but I am writing on the whiteboard. In order for you to answer this question, you need to understand that the distance between successive compressions is the wavelength. You're asked for the wavelength here. And yesterday we learned that speed equals frequency times wavelength. And the frequency of this tuning fork is 256 hertz. So we know that if I want to find the wavelength, I'm going to have to take the speed divided by the frequency. I know the frequency. What don't I know? Well, I don't know the speed. But I can find the speed because I know the temperature of the air that the sound is traveling through. So my first step is actually going to be to find the speed by taking 331 plus 0.6 multiplied by 25. Didn't we already calculate this number? Wasn't that the answer to question 1? 346 meters per second. So the speed that the sound is traveling through the air at is 346 meters per second. We can take that and put it into the universal wave equation, resulting in the speed of 346 meters per second being divided by the frequency of 256 meters, 256 hertz. So 346 divided by 256 gives me a wavelength of 1.35 meters. So just try to visualize what that means. You can't see the air, but if I were to estimate the wavelength of this longitudinal wave, I would estimate it to be 8 centimeters. That's how far apart those compressions look to me on this spring. I don't know that that's 8 centimeters, actually. Let me just check. It's 8 centimeters. If you could see the air molecules and the pieces of the column of air that is coming out of this tuning fork, you would discover that there's a column of air squished together, and 1.35 meters away, there's the next one. Any questions with 3? Okay. Number 4, well, resonance. We'll get to 4 in a second, but resonance is closely related to exactly what we're talking about, especially when you're talking about resonance in air. If a tuning fork has a frequency of 128 hertz, don't worry about the word resonant. Why does it produce a sound wave with the same frequency? I know this is a weird question. I'm asking you, why does this tuning fork that says 128 hertz, why does it produce a sound wave of 128 hertz? I don't want you answering it by saying, because that's what it says. What is this tuning fork doing to produce that frequency? Any ideas?
Well, if you hit it like flat on the table, it wouldn't make as much of a noise if you hit it like sideways, so it's like the sound would be bouncing between.
Well, I'll tell you what, if I do this, that's 128 hertz. That is 128 hertz. If I do this, that's 128 hertz. It's just louder. If I do this, that's 128 hertz. If we had some kind of device that could read the frequency, other than just, if you're musical, your ear, you'd get 128 hertz all the time, no matter how I hit this. And the question is, why? Do you know, Alex?
Is it vibrating 128 times?
It's built with a certain length so that it vibrates with a certain frequency. Just like a pendulum with a certain length will have a certain frequency, these tines, that's what these are called, T-I-N-E-S, these tines oscillate with a certain frequency. They have a natural frequency, and that's called the resonant frequency. So the answer to this question is because the tuning fork is vibrating at 128 times per second. And that means that these two tines are going back and forth in the air 128 times per second, which means they're banging on air molecules 128 times per second, which means those air molecules are going to be vibrating back and forth 128 times per second, which means when that collision finally happens between air molecules in a compression and the surface of your eardrum will be being hammered away 128 times per second. The reason why humans can't hear certain frequencies is because your eardrum is just not capable of vibrating at that frequency. Your eardrum is this really an amazing device that can vibrate at low frequencies and high frequencies, but there's a certain range. Okay. I have a difficult time hearing this. I can't hear it anymore. Can you still hear it? Okay, so I know I'm deaf in one ear. That's not what I'm talking about. As time goes on, parts wear out. Right? I don't know too many people that are driving the same car that they were driving 30, 40 years ago, because things wear out. Same thing with the human body. Your ears deteriorate. So that range of wavelengths that you can hear is going to start doing this over time. Not for a long time, but when you get older, your range of hearing will decrease. And you'll discover that some people, when they're talking to you, you can hear them perfectly well. And others, it's like, stop whispering. But they're not whispering, it's just you. All right, now we're going to talk about resonance. Resonance is the process of one object vibrating with its natural frequency, causing another similar object to vibrate with its natural frequency. I have a perfect example of this. Unfortunately, I don't have the car anymore. I had a 1990 Ford Tempo. And sometimes I would drive it faster than I probably should have been driving it. If you drive that Tempo, my Tempo, at about 118 kilometers per hour, it is smooth as silk. It's so smooth. Nothing is vibrating at all anywhere. But you go up to 118, from 118 up to 120, and the dash starts bouncing around. Okay. You go back to 118, nothing. You slow down to about 115, the dash starts bouncing up and down. And the dash had a couple of resonant frequencies. The dash had a natural vibrational frequency of about 120 hertz. And apparently when I'm driving at that speed, the tires have some kind of frequency. I shouldn't say hertz. It corresponded to 120 kilometers per hour. But whatever the rate of rotation of the tires was at 120 kilometers per hour, that was a natural rotation that dash could vibrate at. And the same with whatever the rate of rotation of the tires at 115 kilometers per hour was. My dash had a natural frequency. I taught for a couple of years in Stettler a long time ago. When a train would go through town in the afternoon at a certain speed, the goalposts on both ends would start doing this, and you would hear this. They would start whistling. But it only happened when the train went through town at a certain speed. And we figured that what was happening was it was vibrating the ground, and the ground was vibrating, and the ground was vibrating, and it got to those two goalposts, the two goalpost stands, and they had a natural frequency that vibrated the same way. You can try a very similar experiment, well, similar idea but different setup. And I'll maybe set this up next week and we can try it. You take a piece of string, pull it fairly tight, and hang a bunch of pendula from it. And take this one and start swinging it back and forth. And what you discover is this one doesn't swing, this one doesn't swing, this one doesn't swing, but this one swings. Because pendula have a certain frequency, right? Based on the period. The period is 2 pi root L over G. So a certain length will have a certain period. If I swing this, and this period is 1.1 seconds, but the period of this is 2.1, this cannot be starting to swing because of this. They don't match up. You're trying to get this to swing at this period or frequency when this doesn't want to swing at that period or frequency. So I showed you this yesterday, but I will show it to you again. I'm going to put one of these on one side of the room. I'm going to put another one on the other side of the room. Right now, neither one of them is making any noise. So why does a tuning fork struck cause an identical tuning fork nearby to resonate? Because they both are capable of vibrating at that frequency. And it's the air that's making contact. What's happening is this tuning fork here, when I strike it, it causes the air right next to it to vibrate back and forth with whatever this frequency is. And through that chain of events called a longitudinal wave, that collision with that frequency continues to spread out through the air until it finally reaches the tuning fork over here. And when that air that's still vibrating at the same initial frequency starts to hit this tuning fork, it vibrates with that frequency. Now what we're going to do is talk about beats. So I've got these two tuning forks and they are identical. And what I'm going to do is get them both going at the same time. Big deal, right? What I'm going to do now is I'm going to change one of the frequencies. You hear that? That's not your imagination. It's going loud, quiet, loud, quiet, loud, quiet. There's some vibration going on because of these magnets. Okay, and we have to wait for that vibration to go away. So let me do that again. Do you think it's a longer delay this time than it was before? Let's try it here. Is that bothering you? A little? It's weird. It is a trippy? Imagine living with that, eh? Everything is... What about if I put it up very high? So remember, I'm changing the frequency of one of these tuning forks. I'm going to try putting this on this one. I don't like that weird vibration that's happening here. And we'll give you a break and hit these guys a little bit. It's there, right? It's just this wobble. Now, I don't know if you can appreciate this, but when I put this up here, do you agree that I would be changing the frequency of this tuning fork by a lot? Intuitively, I mean, if I put these down here, do you think it's likely to change the frequency very much? So when I put them here, the frequency of this tuning fork is not going to change that much. I don't know what that is. I'm going to do that again. I'm going to change the frequency even more. There's more of those increases and decreases. And I'll explain what's going on in a second, but I'll just start by telling you that if the two frequencies are the same, you don't hear anything weird. You just hear that tone. If they're off a little bit, you hear an increase in volume and a decrease in volume that happens over a long period of time. But as the frequencies get bigger and bigger in terms of their difference, you start to hear that happen more rapidly. And this is what's called a beat frequency. We have yet to study interference of waves, but when we do, you will understand, and I'm going to teach it a little bit to you right now, that waves can interfere constructively or destructively. And as two sound waves go through each other, if the compression matches up with the compression, if the compression of one wave overlaps with the compression of the other wave, then you hear more sound. It's louder. On the other hand, any place you have a compression of one wave overlapping with a rarefaction of a different wave, they cancel each other out. Are you with me here? Now, if the two frequencies are the same, then they're always going to be in sync. The compressions will match up with the compressions, the rarefactions will match up with the rarefactions, and you just get a louder wave. But if one of them is slightly behind the other, and you can look over here at this model, imagine that I have this, but I have another one traveling behind it. If the other one is traveling a little faster, if those compressions get a little bit closer together, let's just say, then you're going to have regions where the sound is louder and regions where the sound is lower. And that has to do with the difference in frequencies. Specifically, the beat frequency is the difference between the two frequencies. If I had 5 hertz and 4 hertz, they differ by 1 hertz. So what I would hear is a beat frequency of 1 time per second. The answer to this question is 1 hertz. If I go back over here to this demonstration,
The balance between them.
and we estimate we'll do that again. I would estimate that to be 3 per second. Like I'm watching your hand and you're going, I don't even know if you were doing that intentionally, but you were keeping time to the beat here. I would estimate that to be about 3 beats per second, which means, everybody, that if this tuning fork is 250 hertz, this one is either 253 or 247. They have a different frequency by the beat frequency. That's how far apart they are. So now we can answer number 2. If the frequency of one wave is 4 hertz and the frequency of another is 6, what are the beats that are going to occur? Well, it will be 2 beats per second, the difference between the two. And number 3, if you hear, this was totally unintentional. Honestly, I did not pick the numbers that I just said because of this. I didn't even read this today. This is from a lesson that I've last looked at maybe 3-4 years ago. So that's spooky. If the frequency of one is 250 and we hear a beat frequency of 3 hertz, I didn't plan on putting these magnets here to get 3 hertz. Then what are the potential other frequencies of the second tuning fork? Well, they have to have a difference of 3, and one is 250, so what are 2 numbers that would have a difference of 3 with 250? One of them is 253, one of them is 247. Capiche? Sorry if that lesson was a little awkward without using the smartboard, but I have to fix something in my software. You have an assignment. Most of this assignment deals with the speed of sound in air, but some of it deals with the universal wave equation. Some of it deals with beats. Some of it deals with resonance. Okay. And I hope those slinkies that gives you a better understanding of what a transverse and a horizontal and a longitudinal wave is. Okay, so get to work, please. You still have about 15 minutes or so.